non-neighbors at the parent level, because once you divide them into children, you check if they're neighbors. If they're non-neighbors, you do the calculation. If they're neighbors, which means it's inside this circle, then you push them back into the stack so they get divided again. So that means everything that's pushed into this stack is not a neighbor. So you satisfy this parents neighbor criteria because, so if it's pushed into the stack, that means it is your parent's neighbor, because at the parent's level, it's neighboring, so you push it into the stack, and then you subdivide, so you're looking at the child, and so it satisfies this first criteria on this side, saying it's your parent's neighbor. That's sort of assured from the fact that you are pushing your parent's neighbor case into the stack and popping it. So then, for the cases, once you have those cases where you're looking at the children of the neighbor of your parents, then all you need to do is determine if it's non-neighbor. So that you just need to determine at this point, at every level, that they are not neighbors. If they're neighbors, you leave it for the next round, and then you subdivide again. So that's sort of an implicit way of satisfying this parents, neighbors, children that are not neighbors by, this is more of a computer science kind of technique, because I'm using terms like stack and pushing and popping and tree traversal. So for someone that's in computer science, this may come more natural to you. Those of you that are in more like math and engineering, maybe this one is more intuitive to you because it's just integer manipulation. But for this one, it's more of an idea that's more common in computer science by pushing and popping the pair of the cells and having this conditional for calculating or satisfying the criteria. If it doesn't satisfy, you leave it to the next round. But the good thing about this method is that you can do the following kind of grouping of points. So say that you had points that are distributed on like a circle, and inside it was empty. So say that you had this kind of distribution. Say that you partitioned your domain and created boxes that are rectangles and have a tree made of boxes that are distributed like this, and you created a tree structure like from these boxes. Then it's difficult to use the parents, neighbors, children's, non-neighbors if the boxes are rectangle, because your neighbor could actually be too close for interaction. So say that all these boxes were very thin rectangles. The one that's 2 boxes away from you could still be quite close and not satisfy the Taylor expansion criteria that we mentioned yesterday. So you need them to be far. And this notion of neighbor boxes is not directly a measure of distance unless your boxes are completely square. If your boxes are square, then in each direction, if they're the same number of boxes away from you, that means they're the same distance away from you. So you won't have a problem with the distance. But if they have this strange shape, then you have a problem relating the neighbor boxes to the distance. But in this case, what you're actually doing is you're not looking at the neighbor boxes directly. You're actually measuring the distance and comparing it to the size of your box. So this RT is sort of the radius of your target cell, and your RS is the radius of the source cell, and R is the distance between those two cells. And so since you're using this distance criteria directly to make this decision, you are actually able to use strange shape cells. To do this in this approach, you will need to investigate a larger area of neighbors of your parents. So you can also do it in this index tree approach. You can also use a distance-based criteria for neighbors, not just if the box is neighboring or not. But then you need to search for more boxes because some of them could be outside your direct neighbor space and they could be more far away. So you'd have to examine more things to determine this. In this case, it's sort of an optimal way of examining boxes because it doesn't look at unnecessary boxes. Whatever is inside this stack is sort of inheriting the list of things that need to be examined from the parent. So the parent has already made a decision of what can already be calculated. So whatever it pushes back into the stack is something that absolutely needs to be examined for this criteria. Everything else has been already processed because of these two other branches. But in this case, you don't know a priori what will satisfy this criteria. So you will need to investigate a large neighborhood without knowing whether it's necessary or not. So there are these other advantages and disadvantages of both cases, but it's I just wanted to mention that the linked tree approach does not necessarily have a disadvantage or an advantage. It can do the M2L finding. It just does it in a very different way, which has its own advantages. And if you do it this way, the programming is probably much simpler. So today we will do it this way. In the future, you could try to do it this way. It's not so complicated as well. You can do it in like a few lines of code if you just code this mechanism. But today we will try to do this version. Okay, so I think now it's about the end of the first session. So we will take a 10-minute break, and then the next 3 sessions will be hands-on sessions to code everything we've described. So I think you have all the ingredients, and I will try to go slow. I will do also the same thing I did yesterday. I'll show my screen and start from like very simple tests and build up all the modules that I need, and then finally group them together to make the final code. And everything I will also upload today to the Google Drive again. So if you don't follow, you can always review. Go home and review what was done from all the uploaded material. Okay, thank you. Okay. We're going to start the hands-on session, but I want to make sure everyone has the environment properly set up. So let's do a few checks. So is there anyone that's not logged into a machine that can compile a C code, or is other than the people that want to use MATLAB or some other language? Is everyone okay? Everyone is ready to run something? Okay. So the people who had problem yesterday, is everything okay now? Anyone have a problem, that doesn't have like the square root or that can't compile? Okay, so everything seems okay now. So let's start out by continuing from this morning's lecture by the first thing we will code this morning is the thing we described. So not this one. Okay, so let's try to code something that indexes all your coordinates and gives you back the Morton index. Okay, so this is the first task. We will code something that generates this tree structure. So yeah, like this one. this is our first task for this morning, is to do this sorting. Well, first generating this index array with all these Morton index numbers here. Okay, so maybe we can use part of the code from yesterday. So yesterday so maybe people don't have, does everyone have yesterday's code? Yes? Okay, so in step 1 we created some numbers like this. xi, yi, xj, y. Also I changed the code to 2D because today we will be coding in 2D. So if everyone has yesterday's code in 3D, we first need to change it to a 2D code. So up to here, we don't need anything below here. We just need up to here. Can everyone just create something that looks like this? So this is what we need for today. Maybe we don't even need this distance thing. Without the distance, you know what? To make things simpler, what we actually don't need to distinguish between I and j today. So I'm gonna change to like this. So we have x, y, the two coordinates, and u is the answer we want to determine, and q is the charge. So everyone create an array for x, y, u, q, and fill x and y with the random number. So yesterday I saw one person that had to put like a seed for the random number generator for it to generate a random number. So for this person, I'm going to add this command here. Okay, is everyone okay with this? Can everyone see the code? Anyone that can't see the screen, maybe can. Okay, so everyone's okay. All right, so now we will try to generate the Morton index from this number. So the first thing we need to identify when generating a Morton index is, so we first need to decide which level we're going to calculate. So how many boxes are we going to divide the domain into? And I've already decided to do this example later. So why don't we divide the domain into like a 8 by 8? So we want to create this kind of structure and calculate the Morton index for this kind of structure. So the first thing we need to do is to find the end of the okay. Like this? Okay. Okay, so we know, because we're generating a random number from 0 to 1, we know that this end is 0, this end is 1. So each of these lines, so right here is 0.5, this is 0.25, 0.75, this is 0.125, well, 375, and so on. So we can assume, so we need to do some manipulation of the index. Let's see. So let me pull up as an example. I already have like a Morton index generator somewhere. So let me pull that up from somewhere. No. This is not a very good example, I guess, but yeah, this will do. Okay, so now I'm going to first copy over my other code that already has a Morton index generator. So just wait a few minutes before I... Okay, so this is a function that generates the Morton index. Let me change this to a more understandable. This is in... Okay, this is in 3D, so I'm going to have to do a little more changes so that it's in 2D. Okay, I think this is good now. Okay, so what this is doing is, first I need to calculate a two-dimensional index that represents the two numbers. So I mentioned here, so the first thing I'm generating is actually these two numbers here, because it's easy to know. So from the coordinate, I define, I can determine if I'm 0, 1, 2, 3, 4, 5, 6, or 7. I can determine this number. So this is what we will do first. So let's do a loop. This is like a loop from I equals 0 to n, we loop. Here, we can determine this two-dimensional integer array thing here. So let me bring this here. So ix0 is the number on the x direction, which represents... So how we determine this is, if we divide this by, let's see, if we multiply this by 8 and turn it into an integer, do like a rounding operation. Let's see if what this gives. I'm going to print this and see if it's giving me what I expect. Okay, this is an integer, so I'm going to print with d ix0. So, and I'm also going to print the corresponding x value to see if it's actually giving the correct thing. So what this is doing is, for the coordinates I accidentally overwrote step 1. This should be step 3. Okay, so step 3, oh, okay. It's complaining because I have all this other thing here. So let me just ignore this thing here for a while. I'm going to use this later, but right now it's not compiling because of this, so I'm just going to. Okay, so right now I have this in my code, only this. So what this is doing is it's looping over all the coordinate x's, and I know this is between 0 and 1. So if I multiply by 8, this is going to give me back a floating point number from between 0 and 8. And then if I turn this into an integer, hopefully it will turn into numbers from 0 to 7. So this is what I'm hoping will happen. Okay, so yes, now it gives me, so see, if this number x is small, it gives me back 0. If it's close to this side, it gives me back 6, 4, 1. So these are giving me the numbers that I'm showing. Let me show this slide here. Okay, so it's like these numbers here on the left side are showing me these numbers here, because if the particle is here, then it will return 6. So now I have these numbers here. I can do the same thing with y to get these numbers on this side. Once I have these two numbers, I will use these two numbers to generate the Morton key. Okay, so now I use the 1 index and change this to y. And now I will print both the numbers and also y. Let's print two integers and the x and y like this. Okay, so yeah, maybe I'll split the screen again, so those of you that want to see the code can continue to see the code, and I will use this side to execute the command. Okay, so now these are the y coordinates, and we see the numbers corresponding to the y integer. Now we have the set 0, 3, 6, 2, 4, 0. These are the x and y, two sets of numbers that we need to generate the Morton index. Okay, so now going back to this side, we will bring in this function which generates a Morton index. So let me copy this over, and I will explain to you step by step what this is doing, so don't worry. Okay, so now some of you may be seeing symbols that you haven't seen before when you are coding C. So let me give you an explanation of what these symbols are. So the key, it says key. The key is the index, that Morton index that we want to generate. I'm calling it key. So to generate the key from these two pair of indices, ix0 and ix1, first what we do is we take, sorry, this is actually generating the ix from the key. This is doing the other thing. I think I took the wrong code. Well, maybe I should just write what I need to write from. Yeah, this. Let me go back and find the correct code. It's this one, okay. Okay, so again, this is, I just brought this in from 3D code, so I need to change it back so it's okay, so first we need to determine at what level we want to construct the tree. And so according to the picture I was showing here, so this one, what level is this? So if we divide it once, it's level 1. If we divide it twice, it's level 2. And this is being divided 3 times, so it's level 3. So we want to build a level 3 tree. So I'm setting the level to 3. And then I'm looping over the levels so that yeah, let's set the all right, I'm just changing a little bit the format of the code because this was written in a different style. Okay, so what I want to generate here is I want to loop over, so D is the dimension, and this IX thing should be here, and this should be taking the modulus. Okay, so first I need to explain what this is doing. So I need to bring up the figure where it's manipulating the bits, this one. Okay. So this is slightly difficult to see. Yeah, but I guess it's okay. So first we have the 2 numbers, and we need to shift them and interleave them. So when we interleave the bits, we need to have x, y, x, y. So basically, first I need to have all the bits in the y being interleaved with all the bits in the x, and then start from level 1 and keep pushing them to this side. So in this operation here, I start from level 0, then I first look at the index of ix, and when d is 0, I'm looking at the x index. So when I take this percent thing means it gives you back the number of the first bit. If you if you mask it like this, then it will give you back the number, this first number here. And then what I'm doing here is I'm shifting the bits. So every time a level increases, it shifts 2, right? Every time the dimension increases, it shifts 1. So this number here is how much I need to shift the numbers. And this one is just extracting, this %1 will just extract the bit. So if the current bit I'm looking at in IXD is, I need to actually change this NX to IX. So what this operation does is it just shifts the entire bit 1 level down. So every time I'm looking at a number, I am looking at, so what I'm doing is I'm looking at one bit in IX, and then once I'm done looking at it, I shift that bit this way. So I'm looking at this first bit here, and then I'm putting that into the proper position by shifting it 2L plus D bits. And this, when you want to move it this way, you do this signal. If you want to move it this way, you use this signal. So basically, these are bit shift operators. It just shifts one bit in some direction. So if I do this, I should get this 1 1 0 0 1 0. This is it may look like strange operations to you now, but let's check if this is really generating what we need. Okay, so actually I need to put this whole thing up here, and let's check if it's, by printing we can check if it's really generating what we think it will. So it's very easy to check this, so that's good. Okay, I just need to print I here because this time I'm using I for the, I is not initialized, so let's make sure I is initialized, and then we keep pushing the bits into it. Oh, sorry, I think this should be 2, yeah. Okay, so let's check if let's check if this works. Why is it printing only one number? Ah, sorry, yeah, I can't use the same I, can I? Okay, that was my mistake. I should actually put like index or something. Okay, so let's try again. Okay, now why is oh right, so I'm printing IX, but IX says it's 0 now because so remember these two had numbers in them, but when I do this operation, I'm actually changing the value of IX, and every time it shifts this way, the number gets smaller and smaller until it gets to 0. So eventually, by the time I'm done with this operation, both IX0 and IX1 become 0. That's sort of another way to confirm that I did it correctly. But let's make sure that IX is preserved by maybe I can copy it to some other number before I manipulate it. So say that before I do this operation, I'm going to say, I'm going to save this to some, maybe IX2 or something. Okay. So I'm going to put IX inside this IX2 number so that it doesn't get destroyed. Okay, what? Okay. So now I'm actually showing the original IX numbers along with the. Okay, now we can check if it's correct or not by comparing it to this table. So let's move this over a little bit and see if it's correct. So when x is 0 and y is 3, it's returning 10. Is this correct? X is 0, or sorry, I think I flipped the x and y because, okay, if this is x and this is y, this is correct because 3 and 0, it's 0, right? So let's pretend this is x and this is y. 2 and 6, 28. Okay, so it seems like I programmed it the other way around. 0 and 4 is 16. Okay, so I just need to change the x and y order. Or I can just pretend that the first number is y. But yeah, just for the sake of completeness, let's do it the proper way. So I am going to, no. Okay, so I think what I did here this assumes that the first number is y. Okay, so it's just a definition issue. The first number is y. Let's change this so that it flips. So when d is 0, it should be 1. So why don't we just do like 1 minus d here? Then it should flip the number, I think. Yeah. Let's try this. Oh, sorry. I'll leave this one open. Oh. Did I change something? Oh, what happened? I thought IX2 disappeared. Yeah, I thought I wrote this thing here, but it seems like I erased it accidentally. Okay. No? Ah. Okay, now it should be correct. Well, correct in the sense that the first number is x. Okay, 0, 3, 0, 3, 5, 6, 2, 6, 2, 44. Okay, now it looks like the picture that we imagined in our heads. Okay, so now we have a function. I know it looks strange, but you'll understand when you understand bit shift operators. So the strange signs are this percent thing and this double chevron thing, but they're basically, these are bit manipulating operations that you can use, because that's exactly what we're doing here. We're just, sometimes you want to operate on individual bits or move them around, not just multiply or add to the numbers. So these are bit integer operations, and by prescribing level 3 and dimension 2, we get these numbers. If this were a different level, so if I said this was level 4, this will give me totally different numbers. So this is an input parameter to this generation of the Morton index. Maybe we can make this into a function so that we don't have to look at this every time today when we manipulate all these bits. So let's turn this into a function that gives back the ix2. So now let's call this let's see. So which part should, so let's delete this ix2 thing because we don't need. Okay. Now I think from here to here should be the function. And I think making this, so let's say, so I'm going to move this somewhere else, but I'm going to write it here for now. So you can see, let's call this like a get index function or something. And the input parameters are this ix2. This is the input. And also level. Let's say we want to specify the level here. So we can say, you know, we specify the level somewhere else, but then we're going to input this into the function. So when we call get index, it's going to look like a call that looks like this. And then we're going to move all of this here. And this needs to return actually an integer I, right? So int index, it returns an index. Okay, so this function, when we call it, will return the index value. Yeah, so we need to make it, we need to pass the pointer so that it can change the value and return it. If we don't have this and star here, it won't be able to return a value. So this is just how the C language works. Okay, so now I'm going to move all of this to the somewhere else. So all of the get index thing that we just wrote, this thing I will move maybe like up here or something, so that, okay, so get index is defined here. So every time we call this, we can get the index from the ix. Okay, and now, since ix won't be overwritten, actually we can see if this still works by printing ix. Ix won't be destroyed this time because it's inside the function. So if ix is being changed inside the function, then I think I defined level twice here by accident. Okay. Oh. Yeah. Yeah, we need to initialize index and then okay, now oh, it's still return. Okay. Yeah, because it's an array, it's actually still returning the manipulated numbers. Yeah, that's okay. So now we have a function that correctly calculates the Morton index. Okay, and now by assigning this to actual array, so say let's put this inside an array, not just throw away the number every time it's generated. Let's actually store this index in an array called index, and keep the number in like where's the picture? So like this, we want to have the array like this with all the numbers, and we will call this index n. And now we just need to pass like this, and then we can print index I here for each x and y. Okay, let's see what this one prints. So step 3. Oh, okay, so oh yeah, okay. This should be, this should be the ith index. Oh, what happened? No. Okay. Okay, good. Now it's working. So before I was passing the first pointer. Now I'm incrementing the pointer by 1. You can also write this like. You can also write like this. So this will give you the same answer. So you could either write index plus 1, or you could write you could actually index the thing and then pass the pointer. So this and thing turns it into the pointer of that index inside the array. Okay, so now we have something that can generate and put it inside the proper index array. Okay, now we're generating index. So now, what was the next thing we wanted to do? So now we are able to generate these numbers here. Okay. So another component we want is to go the other way. So from the index, we want to be able to calculate back the two-dimensional index. And so the function I had earlier was actually doing that. Let me pull that back. So where was... maybe I should just leave this open and open something else here. Okay. Okay, now I'm going to add back this function here that calculates So this one calculates from the index, the 1D index, the Morton index. It calculates the 2D IX